1. All right, so we know the definite integral can help us find area, and we know that area can help us find the definite integral, but they're not the same, are they? No, 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 no. The definite integral does always give us the what? What does it always give us? The net accumulation. Very, very good. Okay, so thanks to Hank, I got my folder to open, and I got my calculator ROM file to load. So thanks, Hank.
Yes, sir.
Yeah. Okay. So here we go. An example 4. You're going to have questions where it's going to ask you to find the area. And later on, you're going to have questions that's going to ask you to find the volume. Area and volume have to be positive. And whose job is it to make sure it's positive? Yours. Okay. So it says to find the area bounded by the parabola, y equals that, y equals that, x equals that, x equals that. So when it asks you to find area, you're going to be given enough information, unless it's an improper integral, we'll talk about that later, to actually have boundary lines on all sides as if it were like a country on a map, like Ukraine, right? On a map. Okay. Supposedly tomorrow's the day. I know.
Yeah.
All right. So the first step, once you realize that it's area, is to identify the region. Okay. Identify the region. So let's do it without a calculator. If it's without a calculator, then you're going to be given curves that you're expected to know what they look like, transformation of parent function. So I'll do that right here, kind of in the central area here. So we need an X and Y axis. So there's the Y axis, there's the X axis, X squared minus 1. That's our old friend, Mr. Parabola dude. And he opens up and his vertex is there at 0, 1, right? So there's that. Y equals 0, also known as senior X axis. From X equals 0, so that's the Y axis, to X equals 3, okay, which is another vertical line. Now, the question is X equals 3 to the left or to the right of the intersection point here? Well, it's to the right of it, yeah. So you can kind of look at X squared minus 1. If you set it equal to 0 in your head, the X-intercept is what? If you don't do it in your head, set it equal to 0, right? And you'll get X equals plus or minus 1. So it is important to know where the X-intercepts are. So in this case, we know that X equals 3 is somewhere over here. So I'm just going to draw it right there. All right, now the region has to touch each of the curves at least once. And there might be more than one region. In this case, do we have more than one region? Yes, we have this region here, and we have this region here. So if I were to just straight out integrate from left to right from 0 to 3, it's not going to give me the area, is it? It's going to take the region that's below and assign a negative value, the region that's above and assign it a positive value, and we're going to get the net. So if it says to find it without a calculator, then we've got to set up an integral that'll give it to us. All right, so let's go ahead and do that. I'm going to call it A for area. And the first region is going to be from X equals 0 to 1. And if I integrate from 0 to 1 of the curve, right? The curve is X squared minus 1 dx. That's going to give me a negative value. So we said that there's 2 ways to make that region positive. What's one way? Good. That's the way I would recommend. Just flip your intervals of integration, integrate backwards. And when you do that, it prevents you from having a negative lingering out front, because a negative term can sometimes get lost, especially when doing things by hand, because you can fail to distribute it accidentally. But if you wanted to go from 0 to 1, you can just put a negative out front. All right, so that's the way I like to do it. And then plus, we'll pick up now from 1, and we'll integrate to 3 of it's the same curve. It's X squared minus 1. All right, so there's your setup. Now, if this were for your response question, you would likely get like at least 1 check for that, sometimes 2, depending on how it's partitioned. Okay. Now let's go ahead and use the fundamental theorem of calculus. Find the antiderivative and evaluate it. So the first one, we get 1/3 x cubed minus x. Don't need the plus c. We'll evaluate it from 1 to 0. Hey, and it's the same antiderivative, isn't it? 1/3 x cubed minus x from 1 to 3. All right. And that would get you another check on a free response. And now plug in the top minus plug in the bottom. Plus plug in the top minus plug in the bottom. I'm running out of room. There we go. So here we go. Plug in the 0 and you get 0 minus, oops, well, that's the first parentheses. Sorry, that's 0 minus plug in the 1 and you get 1/3 minus 1. So if you want to color code these, right, there's that. And that becomes this. And luckily, here's where I'm saying it's nice to have not negative signs in front, right? If this second integral, let's say, we put a negative in front because we wanted to make it positive that way, that would be a negative here. And then this would have to be a negative here. And notice if we didn't put brackets or parentheses there, it would affect those two terms, right? So that's why it's nice to have plus signs. All right, now in the second one, I'll plug in the 3, and 3 cubed is 27, divided by 3 is 9 minus 3. Plug in the bottom, and you get 1/3 minus 1. Okay. Now, if this were a free response, would we have to do anything other than that? No. If we're confident that that is in fact a positive number, we could stop right there. Okay. And that would get you another check for the final answer. Okay. So that could be potentially worth 2, 3, 4 checks out of 9 on a free response. Not that difficult, but we did need to know the graph. We did need to know the x-intercept. And the notation is spot on, right? Okay, now if this were a multiple choice, up to this point, we're getting 0 checks, right? Boy, that seems like quite a contrast. And we need to keep going, right? So let's keep going. So we get a negative 1/3 minus 1, that's going to be negative 2/3. And then plus 9 minus 3 is 6. 1/3 minus 1 is again a negative 2/3. And so we end up, and this is carefully, right? We don't take this step for granted. 2/3 plus 6 plus another 2/3. So that's going to be 6 plus 4/3. We added the fractions first. And now 6 is how many thirds? 18, right? So 18 plus 4, 22/3. Okay. And again, if this were a non-calculator multiple choice question, that would be the answer. And you would get 1 check for all of that instead of a free response where you can get up to 4, right? Yeah. The only trade-off is if it's a multiple choice, you can be a little bit looser with your notation because you're not losing points, but you don't want to get too loose with your notation that you trick yourself, right? All right. And of course, since we're going to do it on the calculator, this is approximately what? 7.33333. Okay, good. So that would be that. Now let's say that this showed up on a calculator portion of an exam, whether it's free response or multiple choice. Well, let's do free response. Okay. If it showed up on a calculator portion of a free response, do you need to spend all this time doing it this way? Which you certainly could, right? You can still do it this way. But no. There is a way on the calculator to nuke it so that it's all positive, and it's the, absolute values. So here's also what you'd have to show. We're going from x equals 0 to 3. Okay. The area then is going to be the integral from 0 to 3. We'll just go straight across from left to right by taking the absolute value. I don't want to put f of x there because the function is now called f of x. Okay. If it were called f of x, I could just put f of x there. It's x squared minus 1. Boom. And then take dx, right? So again, we're taking the absolute value of the integrand, not just the absolute value of the answer. That makes it all positive first. And that would give you a check for the setup. And now we go to the calculator. And remember, how do we get the integral to show up? Math 9. And we go from 0 to 3. And then the absolute value is either alpha window 1. Yeah, alpha window 1. Again, alpha window 1. We might try that cheer at our first spring pep rally. It is March 4th. Thank you. I sent them to Bendele. Yeah. Math number one. 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 So that's the better math cheer. That's another way to get the absolute value, right? Math number one. Two more. Two more. Was there a possibility of y'all not doing it?
Well, we got kind of laid off. We got fired.
Oh, I didn't realize that. I thought you had contracts for the year.
This is okay. No, this is where you climb on top.
All right. So ready? 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 We got the absolute value. And look, all we do is hit enter. And guess what it gives us? Yeah, 7.333. Now the calculator is doing it numerically, so it doesn't hit the nail right on the head, but to 3 decimals, it's the same, right? Yeah, there you go. So more than one way to do the problem. The strategy is knowing, when to use which method, and of course, how can I do it and still get full credit? That's what we want to do. Not just get the right answer, but we want to get full credit for it. So notation. And then the answer. All right. So I'm not going to do the next one. Example 5 is kind of the same thing. Just another opportunity to practice. So we're just do that on your own as a bonus one. We got the idea. We got the concept down. Yeah. We don't have time to mess around. All right, cool. Comments or questions on that? Using the integral to help us find the area. Finding the area exclusively on the calculator. Okay. The part in the cap broke off, which is fine. As long as this part doesn't break off, I can still charge it. Okay, cool. Letter 6. Let's do this one. Without a calculator, find the area of the region bounded by the x-axis. So I did read the word area, didn't y'all?
Yes.
Yeah, so it's our job to make sure it's positive. The region is bounded by the x-axis, so that's y equals 0, and the function -20 over x squared plus 1 on the interval from -1 to 1. Use symmetry if you can. Okay, so I wrote this question because a question like this appeared similar to this on a calculator portion back in the day when I was grading AP exams. And of course, if it were a calculator question, let's just see what it would have done. Most kids right away, when like, ooh, I can use the calculator, they go right to graphing it, right? I like the upside down glasses. So let's break the rules here and go to the calculator. Alpha y equals, boom, -20 over x squared plus 1, right? Most kids know that when you want to graph something and you don't know what it looks like, you can do zoom 6. So zoom 6, standard viewing window, and they look like that, like that. And a lot of kids are like, oh, okay, I know what that graph looks like now. It's doing this, and this must be the volcano graph where I got a vertical asymptote there, right? A lot of kids did that, right? Vertical asymptote. Okay. And I'm going from -1 to 1. Okay, so and the x-axis. So I'm finding this area. Whoa. Well, how do you find the area going up to a vertical asymptote? We'll learn how to do that later on. Sometimes it's finite, sometimes it's not. But this was on an AB exam, and the kids were then like, "What the? How do you find the area if it's going down forever and ever?" And so what did they do? They put DNE and they went on to the next, right? Yeah. Well, that's what happens when you don't think. That's what happens when you don't think, because College Board is going to do something like that. There's not a vertical asymptote there, is there? No, thank you. That was convincing, actually. There isn't? Yeah. No, there isn't. Because you're getting this graph confused with 1 over x squared flipped, right? If you look at the domain, right? This is what y'all are trained to do. Let's look at the domain. Can divide by 0. When is x squared plus 1 0? Never. So the domain is all real numbers. Oh, hey, since it looks, what would be the y-intercept? I don't know. Well, what's y of 0? What do you get when you plug in the 0 for x? -20. College Board, you sneaky fiend. What they did is they came up with a graph that that's not what you would have called. All right, I was being polite. Yeah, they came up with a graph that looks like this. It's almost like an inverted bell curve, right? And the y-intercept just happens to be off the graphing screen. So they knew that it was going to be,
Zoom fit.
Yeah,
Zoom zero, zoom
right.
zero.
Exactly. So anyway, if this is a no calculator question, oops. If this is a no calculator question, it almost helps you because now you're like, well, I need to graph it myself. So I know it has a y-intercept of -20. Does it have any symmetry, even, odd, or neither? Y-axis origin,
Y-axis.
y-axis symmetry, right? A negative input gives you the same as a positive. So I know it has y-axis symmetry. I know the domain is all real numbers. Is it ever equal to 0? When is a fraction equal to 0? When the numerator is 0. Is -20 ever 0? No. So this graph lives entirely below the x-axis. And what's the end behavior? What's the limit as x goes to infinity or negative infinity? 0, right? Yeah. So there's a horizontal asymptote. So with that and that alone, you should be able to come up with a semblance of what it looks like. Okay. A semblance. And then you're like, okay, from -1 to 1. So here's -1 and here's 1. So I want to find the area of this region. Well, the entire region is below the x-axis, right? So if I integrated from -1 to 1, I'm going to get a negative value whose magnitude is the area, right? So the simplest way to set up the area integral is to just integrate from where to where? 1 to -1. And then I don't have to worry about splitting it up into two different integrals, right? Because the entire thing is negative. If I integrate the whole thing from right to left, it'll make it positive. Good. And so now if I set it up, this is what it looks like. And you'll get a check for the setup. Now, let's do a couple of things. First of all, I gave you the hint to use symmetry. You don't have to use symmetry. But we talked about the other day, if you integrate an odd function with origin symmetry on a symmetric interval, it's always going to be what value? If you integrate an odd function like sine of x on an odd interval, or on a symmetric interval, sorry, it's always going to be 0 because the magnitudes are always going to be opposite and equal. But if you integrate an even function on a symmetric interval, they're not going to be opposite in sign and equal in magnitude. They're going to be the same sign and equal in magnitude. So you can, if you want, make it easier on yourself by doubling the integral on half the interval. Okay. In other words, instead of going from 1 to -1, I could go from 1 to 0. I can find this and double it. Now, why would you want to do that? It's just an option. You don't have to plug in a negative number, which could be nice. And plugging in a 0 can sometimes be really nice. So it's just an option that you have. Okay. And what else can I do then to help me with this problem? The -20, take it out front, right? Get in the back of the truck, in the front of the integral. Very good. And then we're left with just 1 over x² + 1 dx. And now I recognize the integrand as the derivative of arctangent. Okay, good. So if I simplify the coefficient, now I get -40 arctangent of x from 1 to 0. Yes. I'd rather go, well, I'm going to double it. So I can either double it from 1 to 0 or double it from 0 to -1. And I would choose to like get rid of the negative. Yeah. Now you'll see why it's nice not to have the -1. If I then pull the -40 out front, as I like to do, plug in the top, you get arctangent of 0 minus plug in the bottom, arctangent of 1. On a free response, you would get a check for the setup. You would get a check for the antiderivative. And could we stop on this line?
Yes.
Yes, we could. But if this were a multiple choice, we'd have to keep going. So notice if I didn't use symmetry, instead of arctangent of 0, I would have arctangent of -1. Arctangent of -1 is what? Tangent of what angle in the principal value range is -1? Where's tangent -1? It would be -π4, right? So you'd have to realize that, oh, it's not going to be over there at 3π4, and certainly not at 7π4. I'd have to get there by going straight down directly. Yeah. So by not having the negative, you're just like, oh, arctangent of 0. Oh, that's 0, right? A lot easier. And then arctangent of 1, tangent of what angle is 1? Well, yeah, they all have the first quadrant. All right. And now, again, finishing it out, it should be a positive number. Is it? A negative times a negative is a positive. 40 divided by 4 is 10. We get 10 pi. 10 pi. 10 pi. Nice. What if we let pi, what if we come off to the side and we let pi equal q, and then we write our answer as 10q? No. 10q? No, I wouldn't want to do that, right? What would be the only reason to do that? For funsies, so that if someone read your answer, like, what is this, Jackson? You're welcome. See, that's a long way to go. That's a long way to go for some bad math joke. Bad dad math joke. All right. Yeah. 10Q. You're welcome. Yeah. So save those types of shenanigans for the math club meeting, not for the AP exam. Hey, speaking of math club meeting, we got one tomorrow during advisory. Mr. Master Mason is going to be presenting. Yeah. Okay. Yeah. Show up, find out. Okay, cool. All right. Any comments on that? We're shifting gears here now to something very important. We are going to now define a definite integral as a variable function, right? Up to now, our definite integrals have had numeric intervals of integration, and the definite answer that it represented the net accumulation. But we can actually have variables in our intervals of integration. So let's go ahead and define this. The second part of the theorem deals with functions of this form. Let's define big F of x to be the definite integral from some constant a that's in the domain of little f to a variable x of f of t dt. Ooh. Now, what the heck does that mean? Well, first of all, when we define a function, this is our independent variable, yes? And so on the other side of the equation, that also represents your independent variable. So when I change it on the left, that's what changes on the right. In other words, f of 1 would be the integral from a to 1 of f of t dt. F of 0 would be the integral from a to 0 of f of t dt. So it's, in this case, just the upper limit of integration. That's the variable. It changes, right? But we're starting at some fixed x value, call it a. Now, why do we have to use t and dt here? Well, t and dt could be anything that match other than x and dx. Because if that was f of x dx, now if I ask you what's big F of x, well, what's big F of 1? It would be the integral from a to 1 of f of 1 d1, right? You see how that would be confusing? We don't want that to happen. We want to clearly define our independent variable to be the interval of integration. So remember that it doesn't matter what those are as long as they match. That could be f of a dA, f of p dp, f of q dq, whatever. We typically just change it then to t, because we use t a lot for our independent variable when it comes to motion, right? So that's defining the antiderivative as a definite integral to be a function of x. Now, yeah, there you go. Okay, sweet. Let's try it out. You want to try it out? Let's try it out. Here's where these types of questions come in. These make really, really good free response questions or multiple choice. The graph of f of t is given, right? Oh, okay, I see. This is the graph of f of t. This is f of t. So this must be the f of t values, little f of t, and this must be the t axis. Oh yeah, it is. It's defined. Okay. Let big F of x be the definite integral from 2 to x of f of t with respect to t. Okay, so we're starting here at x equals 2. We're starting here at x equals 2, and big F then is going to be the net accumulation under the curve starting at 2 to some x value, okay? It says to use the areas of the regions to find the following. All righty. So notice that the graph is made up of line segments. If you have a graph made up of line segments or parts of circles, you can find the area geometrically. Part A, find big F of 2. Okay. Well, step 1, plug it into both sides. Big F of 2 is going to be the integral from 2 to 2 of f of t dt. The integral from 2 to 2. The net accumulation from 2 to 2. What do you think the net accumulation is from 2 to 2 is? Probably 0. Yeah, because you can't accumulate anything or lose anything for that matter if you let no time go by, right? Nothing ventured, nothing gained, right? It's safe to stay on the shore, but that's not what boats are made for, or something like that, right? Yeah, so in general, the integral from A to A is 0, right? If you want to think about it in terms of an area, the height would be 20, right? But what's the width from 2 to 2? 0, and 0 times 20 is 0. So you can think about it both ways. All right, so that one was an easy one. F of 9, well, that's going to be the net accumulation from 2 to 9 of f of t dt. Oh, from 2 to 9. So now I'm going from left to right, and I'm going all the way up to here. So, wow, is that going to be a positive accumulation or a negative? Should be positive, right? Because I'm going from left to right, and the entire region is above the x-axis. So, in fact, if I can find the area of that region, that's also going to be the integral value, isn't it? Now, you could partition these regions up into however many partitions you want. Like you could drop a line here at 7 and call it rectangle and triangle. Or you can just think of it as a trapezoid laying down. Yeah? So it doesn't really matter. I'm going to use a trapezoid here. So the area of this trapezoid is 1/2 the sum of the bases. And this one is like a regular trapezoid that you studied in geometry. The bases aren't vertically now like they were when we did the trapezoidal rule. They're side to side. So how far is it from 2 to 7? 5. How far is it from 2 to 9? 7. So this is going to be 5 plus 7 times the height, which is, of course, 20. So this is a right trapezoid. And now let's see what that gives us. That gives us 10 times 12, so 120, all right? So remember, for a free response, or even for a multiple choice to help yourself, we write the areas of the regions inside the region itself, and we cycle it, okay? And now I'll come over here, and I'll say 120. And that's it. On a free response, you're getting full credit. You have the notation. I can see exactly where you're getting the 120 because it's a number in your diagram. So check. All right. F of 15. Well, let's see. That's the integral from 2 to 15 of f of t dt. From 2 to 15. Well, 15 is way over yonder. So it's going to be 120. And then if I can find the area of this trapezoid, I'd have to do what? Subtract it because it's from left to right and it's below. Let's go ahead and find the area of this dude. Okay, I'll color him red. Now I'll come down here. I'm going to mark it out here to help myself. From 9 to 15 is 6 units. From x equals 10 to x equals 14 is 4 units. And so the area is 1/2 the sum of those numbers, 6 plus 4. And then the height here is 10 units. So again, I'm not using -10. I'm finding areas, positive values. So that's 5 times 10. This is 50. All right, I think it's right. 5 times 10. Yeah. So now with these two numbers shown in my areas, I'll come over here and say that this is 120 minus 50. And on a free response, you're done, right? Don't do that in your head and say 120 minus 50, that's 63, right? Because you might get it wrong like I did. Plus that number is not showing up in your calculations and you're not going to be indicating your method. All right, so free response, you're done. But of course, that's equal to what? 70 if we had a multi-choice question. So on and so forth, right? So go ahead and do f of 18 on your own. I'm going to do it quietly. I'm not going to pause the video here. If you finish that one, go ahead and do the next one also as well. Bless you.
Thank you.
You're welcome. Don't forget your non-perishables as well. I keep forgetting. All right, so part D, f of 18. You want to show it first. The function is from 2 to x. When x is 18, it's from 2 to 18 of f of t dt. So again, you want to indicate your method. Where's 18? It's way out here. So we have one more right trapezoid. The area is 25. When you have these three numbers in there as positive values representing areas, then when you evaluate your definite integral, you assign a plus or minus sign to them, and those numbers have to appear if you have the hopes of indicating your method. So 120 minus 50, and then back above from left to right, it's plus 25. So you get a check for the setup, a check for indicating your method, and that's also your numeric answer on a free response, but it does come out to 95. Now, the last one, big F of 0. That's the integral from 2 to 0. What's funky about that one? Yeah, it's backwards, right? It's backwards. So it's the opposite of what it normally is. We're watching the film in reverse. So first of all, it's a triangle from 0 to 2, 1/2 the base times the height. The area is 20. But now, since we're going from right to left and it's above, it's going to be -20. Yeah, you got it. You got it. See, that's using areas to find integrals instead of integrals to find areas. It's fun. It's easy. It's easy, right? Yeah. Okay, cool. So anyway, that's one reason why we want to define an integral function as a function of x, okay? And we can actually define the independent variable x to be not just the upper bound, we can define it to be the lower bound we can even define the upper and the lower bound to be functions of x. It doesn't have to be x. It could be like x or x squared. Okay. So we're getting closer and closer to the second part of the FTOC. Now, I feel like I want to skip example 8 and just get to it, but I think it's worth doing, right? Even in our time constraints. So let's do it. Let's let big F of x equal the integral from 3 to x of t squared plus t plus 1 with respect to t. We want to find a simplified expanded version of f of x by evaluating the definite integral. So in this case, I'm not evaluating f of x for specific values of x, like f of 1, f of 3, whatever. What I want to do is actually evaluate the integral. It is a definite integral still, right? So it doesn't matter if those are numbers or variables. If I can find an antiderivative for the integrand, I can evaluate it by using the FTOC. So let's go ahead and do that. Big F of x is going to equal 2, and that'll just be the left side. This is a pretty easy antiderivative to find. Yeah. It's the power rule, right? So 1/3 t cubed plus 1/2 t squared plus t, and we don't need the plus c, and then we evaluate it from 3 to x. Now, in this case, it looks a little strange. It's like, wow, I get having the independent variable as x when it's in integral format, because it's just going to be the upper limit of integration. But right now, it looks weird to have f of x and then a bunch of t variables. You're like, where's the x? Well, we're not done evaluating it, right? Let's go ahead and continue on the right-hand side. We'll plug in the top, right? So for every t, we plug in a what? An x. So we get 1/3 x cubed plus 1/2 x squared plus x. Oh, that turned it into a function of x right there, but then minus parentheses, let's plug in a 3. Now I'm not going to simplify it. I'll just call this 1/3 times 3 cubed plus 1/2 times 3 squared plus 3. Okay. And that's going to be some constant, right? That's some constant. So now I have two ways to interpret this. If I ask you to find, for instance, f of 1, I can either interpret that as the integral from 3 to 1 of this function and do what we did above, interpret it like as areas, or I can now think about it as simply finding the y value of this cubic polynomial, right? It's exactly the same. We're interpreting it two different ways, but I don't want to do that. Okay. What I want to do now is turn around and I want to find big F prime of x. And I know what you're saying. Why in the heck do you want to do that? We just found the antiderivative. Why do you want to turn around and find the derivative, right? Because they should do what to each other? Like, what if you do multiplication and division back to back? Multiply by 5, divide by 5. Yeah, they undo each other. They cancel each other. So if I find the antiderivative and turn around and take the derivative, they should cancel each other out. Well, I don't know. I didn't know I wanted to take the derivative at the time, you know. I'm just taking the scenic route. Let's try it. Let's take the derivative both sides. The derivative of the left side is, you know, big F prime of x. What can we call big F prime of x notationally? Yeah, little f of x, right? Big F by notation is the antiderivative of little f. So the derivative of big F, we could call little f. Now on the right-hand side, we'll multiply and subtract. 3 times a third is 1. We get x squared. Plus 2 times a half is 1, x to the first. Plus 1. And then minus, what's the derivative of this whole dude? 0. So there you go. So we get x squared plus x plus 1. Here's my question. If I told you that I wanted to find f prime of x in the very beginning, that would be the derivative of the left side. I can write it like this on the right. I can write it as the derivative with respect to x of the integral from 3 to x of t squared plus t plus 1 with respect to t. If I would have told you in the very beginning that my intentions were to take the antiderivative and then turn around and undo it by taking the derivative, by taking the derivative of the integral, is there any way you could have predicted what the answer would have been without having to actually do the work? I hope so, right? Because look, we ended up with x squared plus x plus 1. Is that visible anywhere in the original problem? Kind of, right? Kind of. In the original problem, the integrand was in terms of t, but when I actually take the derivative, it was in terms of x. And we know why it was in terms of x. Yes? Because when I actually evaluated the integral and I plugged in the top, the t's became x's, so that when I took the derivative, it became x. Is that a coincidence that x squared plus x plus 1 is basically t squared plus t plus 1 with an x in there? It's not. It's not a coincidence at all. And it's because of the second part of the fundamental theorem of calculus, right? The derivative, remember, is a division process, and the integral is a multiplication process. So just like division and multiplication are inverse operations, so are the derivative and the integral, okay? So what's important, though, for you to end up with the exact same integrand, only as a function of x instead of t, is this. It was important that the upper limit of integration was in fact an x, because that's what changed it from t's to x's, right? It was also important that the bottom number was not necessarily a 3, but a constant. Very good. Because if it were any constant, that would have made that last term a constant whose derivative would have been 0. Okay? And so that leads us to this right here. If f is continuous on the closed interval, then the function f, that's defined by this, big F of x is the integral from some constant a to a variable x of f of t dt. If we define big F to be that integral function, then big F prime of x is equal to, big F prime of x is equal to little f of x, not t. It does change back to a function of x. So this would be the noun format. Here's the verb format. The derivative with respect to x of the integral from any constant a to x of f of t dt is f of x. Okay? They undo each other. The derivative of the integral from a constant to x is just the integrand. All right? You don't have to do the work. Now, can you do the work? Can you actually do it from the inside out? Please excuse my dear Aunt Sally. Yeah. But what's going to happen is you're going to often see that you have an integrand that doesn't have a known antiderivative. And you're going to be expected to find the derivative of the antiderivative. Well, duh, it's going to be the original integrand. Okay. It seems like a duh type of problem. Let's practice it. Let's practice it. Part A. The derivative with respect to x of the integral from 1 to x of secant of t dt. Any guesses? Secant of x. Yes, good. Secant of x. Now, for kicks and giggles, let's verify it. Let's verify it. Let's take the derivative with respect to x of, and let's evaluate the inside. This will be a good review. What is the antiderivative of secant? Well, that's the derivative of secant. Now, remember, if you remember what I told you, the antiderivative of secant is exactly like the derivative of secant, right? Which was secant t tangent of t. The only difference is instead of multiplying them, secant times tangent, they're added together inside of an absolute value behind a natural log, right? Remember that? Remember that? That's the only difference. That's the only difference. All right. Yeah, and then we evaluate it from 1 to x. Make sure you still know your antiderivatives, right? We did that memorization test. Yeah. And now let's take the derivative of that, or let's evaluate it, sorry. Now, before I take the derivative, that becomes the natural log of secant of x plus tangent of x.
course.
minus the natural log of, I'm just going to call this a constant. Are you okay with that? The natural log of a constant is I don't want to write it all out because I know I'm going to turn around and take the derivative of it. The natural log of that constant is a constant. So let's take the derivative now. When you take the derivative of the natural log of the absolute value of blob, what happens with the absolute values? They go away. And remember, it's 1 over the blob, 1 over the blob times the chain rule, the derivative of the blob. Well, it's 2 terms. What's the derivative of secant? Secant x tangent x, just like the antiderivative, except they're multiplied outside of, there's no log. Yeah, okay.
Yep.
Plus the derivative of tangent, which is secant squared, and then minus 0. Now, what can I do to simplify that? I can factor out, and that second term factor, I can factor out a secant of x, and that leaves me secant x plus tangent of x. Oh. And now look at this. Those divide out, and we're left with 1 times secant, which is secant of x. Oh my gosh, y'all were right. Y'all were right from the beginning. But at least we know now, right? And we reviewed a little bit. Yeah. So there you go. The derivative of the integral from a constant that has to be in the domain, from a constant to x of secant of t dt is just secant of x, right? Good. I think we're comfortable now. We don't have to verify it anymore, right? Unless you want to. We won't always be able to. Here, at least we were able to. All right. How about this one? The derivative with respect to x of the integral from 5 to x of p sine p dp. Put an x where the p is and get the square root of x cubed sine of x. Do we put plus c? No, no, no. Not unless off to the side you say c is 0, where c is 0. There's no plus c, because remember, order of operations. We integrate, evaluate, and then the last thing we do is we take the derivative. The c's would have been gone anyway, right? Yeah, there you go. All right, you're so good now. Do this one. The integral or the derivative with respect to x of the integral from pi to x of little k.
What?
I didn't want to say all that.
Pretty sure Ethan was taking it. You should verify this. Aaron, you verify it. No, we don't.
All right, I'm writing down the answer. I'm looking around. Mason, should the derivative still be out front? No, no. Just think of these two things as undoing each other. Multiply by 5, divide by 5, right? They're gone. All right. Is it that easy? Yes. Whenever it's the derivative of the integral and you're going from plain old number to plain old x, it is that easy. But are we always going to be going from plain old number to plain old x? No, no, no. Here's the general form, okay? In general, if we're taking the derivative with respect to x, and we're going from a function of x to a function of x power. So that could be like from x squared to e to the x. Doesn't have to be a number to x of f of t dt. Well, guess what? It's going to be like a combination of the first and second root. We're going to do f of the top. So f of g of x, right? Instead of just plain old f of x, it's f of g of x times the chain rule g prime of x minus, now we'll plug in the bottom, f of h of x times the chain rule h prime of x. All right, here's what it looks like in general. Let's come back to this little innocuous one over here, because here's the general procedure. Okay, whenever it's constant to x, you can just say, ooh, I'm replacing that with x. But here's in general what we do. It's going to be secant of, and you plug in the top, we get secant of x times the chain rule, the derivative of what we plugged in, with respect to x. What's the derivative of x with respect to x? 1 minus, plug in the bottom, secant of 1 times the chain rule, the derivative of what we plugged in. What's the derivative of 1? 0. And what will that simplify to? Secant of x. So really, this becomes like a special case of the general rule. If it's ever from a plain old number to a plain old x, the derivative of the integral is the plain old integrand. But let's try and squeeze one in here. Part A, 10a. The derivative with respect to x of the integral from 1 to not x, but to x cubed of secant squared of t. It's not going to be just secant squared of x, but that would be a great answer choice. Like the first fundamental theorem, we plug this in and we get secant squared of 2x cubed times the chain rule, the derivative of what we plugged in. What's the derivative of 2x cubed? 6x squared. Okay, boom. And then minus, do we even need to worry about the bottom here? Secant squared of 1? Not really, because if we're plugging in a constant, what's the derivative of the constant? 0. Yeah. And the answer is 6x squared times secant squared of 2x cubed. Okay. Now we can actually verify this one. If you want to verify in the privacy of your own home, the antiderivative of secant squared is tangent. If you evaluate it from 1 to 2x cubed, you'll see why we have to use the chain rule. It'll become clear to you. All right. We're going to stop right there. We are going to hustle to finish up tomorrow. We're going to hustle to finish up tomorrow. Now that Hank has all the technology fixed for me, we're going to hustle to finish up tomorrow. And we're going to move on to my favorite section of the whole year, 4.4. Okay. Any other questions besides Ella's? Y'all have a great sea lunch.